The idea is that we know that any function ft can be represented as a0 plus sum n equal to 1 to infinity n cos n omega 0 t plus bn sin n omega 0 t, where omega 0 equal to 2 pi by tau, 2 pi by t, and f0, that is frequency, is equal to 1 by t. And from the equations, we know that a0 equal to 1 by t 0 to t ft dt. It is a0, and an equal to 2 by t sine 0 to t ft cos n omega 0 t dt, and bn equal to 2 by t integration 0 to t ft sine n omega 0 t dt. So the idea of Fourier transform is to find a sinusoidal, is to represent a function as a sum of sinusoidal signals, sinusoidal or cos signals. Okay, now where f0t ft is equal to a0 sum n equal to 1 to infinity an cos n omega 0 t plus phi n, a0 equal to a0, an equal to root s an square plus bn square, phi n equal to minus tan inverse bn by n. This is known as the polar form of Fourier series. Now, as an example, if you see that, let's say that is f0, this is 3f0, 5f0, and 7f0. Now, if you superimpose those and add them, then what you see is the signal at the end. This signal looks like a square. So that's how you can represent as sum of sinusoidal or cos signals as a different waves, different signals that you have learned. For example, if you have only a0, then the wave is like this. I want to match a rectangular wave or a square wave using periodic square waves. So if I take the fundamental, signal or the a0 value only, then what will happen? I will get a signal like that at the top. This signal is not at all representing the square wave. If I take 5 terms, then it is somewhat representing the square wave. If I take 11 terms, it is more closely representing the square wave. And if I take 49 terms, then you can see there is almost no difference between the square wave and the sinusoidal function, sum of sinusoidal functions. Let's not go through that. Now let's come to the definition of Fourier transform. The definition of Fourier transform is, it is f omega equal to Fourier transform of ft equal to minus infinity to plus infinity ft e to the power minus j omega t, where j is the imaginary number, minus root over minus 1 omega t dt. And the inverse Fourier transform is ft equal to f inverse f omega is equal to 1 by 2 pi integration minus infinity to plus infinity f omega e to the power j omega t d omega. Now, for every function there is a Fourier transform, and for every Fourier transform there is a unique function. So Fourier transform uniquely represents the function. Remember these two equations are very important. As you saw in the Laplace transform, it was e to the power minus st dt. In here it is e to the power minus j omega t. And the bounds are minus infinity to plus infinity. Have you understood it? Any questions? Anybody has any questions?
Sir, is this for continuous function or for discrete function too?
It is for continuous function, not discrete function. Discrete function, how can you integrate?
Yes, sir. Yes, sir. We can't integrate that discrete function.
Yes, so it is for continuous function. Okay.
Okay, sir.
Any other questions? And remember that omega is equal to 2 pi f, where f is the frequency. Any other question? Anybody has any questions? Okay. Now, Fourier transform produces a continuous spectrum. Fourier transform gives a spectra consisting of continuous sum of exponential with frequencies ranging from minus infinity to plus infinity. So f omega equal to mod f omega into e to the power j phi omega, where mod f omega is the continuous amplitude spectrum of ft and phi omega is the continuous phase spectrum of ft. Often only the magnitude f omega is displayed and the phase is ignored. For example, if you have the impulse function, then for the impulse function, the Fourier transform of the impulse function is delta t to the power minus j omega t minus infinity to plus infinity dt equal to e to the power j omega t equal to 0, because all other value or at all other places this impulse function vanishes. So it is t equal to 0, so e to the power j omega 0 equal to 1. What was the Laplace transform of the impulse function? What was the Laplace transform of the impulse function?
Sir, 1 by s.
1 by s. So this is the impulse function's Fourier transform. Fourier transform of single rectangular parts. That means it is within minus t minus tau by 2 plus 2 plus t plus tau by 2. So ft equal to rectangle of t equal to rectangle function of t by tau equal to 1 for minus tau by 2 t less than equal to tau by 2 and 0 for all mod t greater than tau by 2. So f omega is equal to minus infinity to plus infinity ft to the power minus j omega t dt equal to minus tau by t to plus tau by t to the power minus j omega t dt, because at all other places the function vanishes. Now if you integrate it, it will be e to the power minus j omega t by j omega minus tau by 2 to plus tau by 2. So if you replace it, if you find the value, it will be e to the power minus j omega tau by 2 minus e to the power j omega tau by 2 equal to minus j 2 sine omega tau by 2. So it is ultimately tau sine omega tau by 2 divided by omega tau by 2. Understood? Yes. Have you understood? Anybody has any questions?
Sir, over here is the Fourier transform of the single rectangular pulses, sir, but why is it being written as omega, sir? That word, I didn't get that point, sir.
Or omega?
Sir, it's written f of omega, right? Acha, sorry, that's the term. Sorry, sir, that's just the term. Got it now, sir.
Anybody else has any questions? So this is how you have to find the Fourier transform of a function. Okay. So understand this example very well. I wanted to find the Fourier transform of a single rectangular pulse and the value I have got. Have you understood? Is there any question? If there is any question, you can stop me and ask me. Now, f omega equal to, this is sinc function, if you remember, is sin x by x. So this is the sinc function. Now, note that the pulse is not centered. This is a sinc function. So sinc function into tau is the value. Properties of sinc function. Sinc x equal to sin x by x. Sinc x is an even function. Sinc x equal to 0 at points where sin x equal to 0, that is sinc x equal to 0 when x equal to plus minus pi, plus minus 2 pi, plus minus 3 pi, etc. Using L'Hopital's rule, it can be shown that sinc 0 equal to 1. Sinc x oscillates as sin x oscillates and monotonically decreases as 1 by x decreases as mod x increases. Sin x, sinc x is the Fourier transform of the single rectangular pulse. So remember the definition of sinc function is sin x by x. Okay. Don't worry about this. Now, properties of Fourier transforms. So, if you have understood, then the property is linearity. Linearity says that ft, if the Fourier transform of ft is f omega and Fourier transform of gt is g omega, then ft plus gt equal to gt's Fourier transform is f omega plus g omega. Also, kft's Fourier transform is kf omega and mgt's Fourier transform is mg omega, where k and m are constants. Combining this, we have kft plus mgt's Fourier transform is kf omega plus mg omega. Hence, the Fourier transform is a linear transformation. Can you prove this? Anybody can prove it. Yes. Anybody can prove it. What you have to do is you have to find the Fourier transform of kft plus mgt. By definition, it is kft plus mgt into e to the power minus j omega t. Now minus to the power minus j omega t, and the integration is between minus infinity and plus infinity. Now since k and m are constants, it will come out, and then ft e to the power minus j omega t and gt plus gt e to the power minus j omega t will remain, and from there you can find the value is kf omega plus gf plus g omega. Okay, time scaling property. Fourier transform of f at equal to 1 by mod a f omega by a. Do it. Prove this. Fourier transform of f at equal to 1 by mod a Fourier transform omega by a. F omega by a. Anybody done? Anybody could do it? Okay, the proof is like this. If I want to take the Fourier transform of f at t, then by definition it is Fourier transform of f at t equal to integration minus infinity to plus infinity f at t e to the power j omega minus j omega t dt. Make the substitution lambda equal to at, therefore d lambda equal to a dt. Then Fourier transform of f at equal to minus infinity to plus infinity f lambda e to the power minus j omega t d lambda by a equal to 1 by a f of omega by a, because t equal to lambda by a. So the proof is this. Therefore, we can prove that it is by time scaling property. Fourier transform of f at equal to 1 by mod a f omega by a. Therefore, Fourier transform of f minus t equal to f minus omega. Okay, got it? Are you following?
So
So answer me sometimes. Time shifting property f of Fourier transform of f t minus t0 equal to e to the power minus j omega t0 f omega. Prove this one.
yes, sir. Done, sir.
Anybody else? So the proof goes like this. So I have to check that Fourier transform of f t minus t0 equal to e to the power minus j omega t0 f omega. So Fourier transform of f t minus t0 equal to, by definition, minus infinity to plus infinity f of t minus t0 e to the power minus j omega t dt. Make the substitution lambda equal to t minus t0, therefore d lambda equal to dt and t equal to lambda plus t0. Then Fourier transform of f t minus t0 equal to minus infinity to plus infinity f lambda e to the power minus j omega lambda plus t0 d lambda equal to e to the power minus j omega t0 minus infinity to plus infinity f lambda e to the power minus j omega lambda t lambda equal to e to the power minus j omega t0 f omega. Any question from this? Just remember the definition and apply your integration rules. That's all. You have to do simple integrations, nothing more than that. Any questions from this? Okay. Frequency shifting function f of Fourier transform of ft to the power j omega 0 t equal to Fourier transform of omega minus omega 0. Prove it. Done?
Doing so.
Okay, do it, do it. All of you do it. Do it in the class so that you don't have to read again. You can do it in the exam directly. Done now?
Yes, sir. Done.
Anybody done? Anybody else done?
Yes, sir. Yes, sir.
Okay. So this is how you prove it. Fourier transform of ft to the power j omega 0 t equal to, by definition, minus infinity to plus infinity ft to the power j omega 0 t e to the power minus j omega t dt, which is equal to minus infinity to plus infinity ft to the power minus j omega minus omega 0 t dt. This will not be lambda, this will be t, which is equal to, now you can replace omega by omega minus omega 0, everything will remain fixed, and you can say this is f of omega, this is f of, this is f of omega minus omega 0. Now, special application, if you apply it to cos omega 0 t equal to half e to the power j omega 0 t plus e to the power minus j omega 0 t. What is this theorem? Huh? What is this theorem called?
Sir, I don't remember, sir, but I don't remember the name, sir, specifically, sir.
Anybody remembers? Is it correct? Is it correct or not?
Yes, sir.
This
Yes,
is
sir.
what is the name of the inventor? De Moivre's theorem, remember?
Yes, sir.
Okay. Now, if we apply it to cos omega 0 t equal to half e to the power j omega 0 t plus e to the power minus j omega 0 t, then Fourier transform of ft cos omega 0 t is equal to half f omega minus omega 0 plus f omega plus omega 0. Euler's formula, and you know sin theta and cos theta. You don't have to go worry about the electronic stuff that much. Just concentrate on the mathematics. Okay, so I will stop today here. Today I will stop here.
Sir, will you share the slides, sir?
Yes, I am sending the slides. Now, so your exam is on, your second exam is from when?
Sir, I think 20th of March.
25th.
25th.
Not 25th, not 25th. Wait.
Sir, from 22.
22, sir.
22,
Yes.
okay. In that case, I won't be available next week. Will be outstation next week. And next to next week is your exam. So your next class will be in April. Okay. Now I don't have much to cover in less. I had to cover the basic of signals, then Laplace transform, then Fourier transform. I have covered basic of signals, Laplace transform maximum 2 months. Okay, so that will be covered in April. Don't worry. So I'll cover my part of the syllabus, and I'm sending you the syllabus. So your next class will be on April. The Wednesday on April. First Wednesday on April. What is the date?
Sir, 7.
7th, yes. So 7th of April is your next class. Okay. And in your next exam, the continuous assessment 2, there will be an introduction to Fourier transform I will give. I'll give maybe some Fourier transform computation I can give, but there will be Laplace transform and the signal part. All of those will be there. Okay.
Okay, sir.
Okay. So next class, next see you on 7th of April. Leaving I am okay.
Okay, sir. Thank you, sir.